We have talked about inferences like hypothesis testing and those intervals calculation. And now we are going to assess the accuracy of the model. So how good is the regression model fit our data? Basically, we have two different methods to evaluate it. Okay, let me start the slideshow. Okay, so we'll start with the some terminologies in ANOVA, analysis of variance. That's what ANOVA stands for. Well, the first one is called total sum of squares, SST, which is the total variability of the sample. Or if you still remember, we talked about this, we mentioned this SYY, which is just this total sum of squares. If you look at the formulation here, this is the total variabilities of the sample. So this is your data minus the mean of the data. So this gives you the total variabilities. And the residual sum of square, we actually talked about this before. This is the error that the model doesn't explain. So this is your data minus the predicted or fitted value for y. So this measures the residual. So this is the residual. You take the square and you take the sum, residual sum of squares. And that's the error the model did not explain. A third terminology is called regression sum of square. So it's another sum of squares. So this is the fitted value yi hat minus the mean. So it measures like how far the fitted value is from the mean. And you take the square and take the sum, that's the regression sum of square. That measures the variability that the model does explain. So this one basically compared the fitted value with the mean of the data. So the mean of the data is nothing but a horizontal line. It's a straight line across the data where this yi hat will, those all lines on the, they all lie on your regression line. So this is measuring how far the regression line from that horizontal mean of the data. And this is called SS reg for regulation, for regression. Okay, I have this small plot to illustrate what are the relationships between these three terms that we mentioned from previous slides. So if you focus on this quantity first, so I'm measuring the data, how far the data, see this is one data point that we have, I call it xi and yi, and how far this yi is from this horizontal mean value of your data, y bar. So this is measuring the distance between this data and data point with this horizontal line. And I just split it into two quantities. The first one is this yi minus yi hat. This yi hat I mentioned, it just lines on this the regression line. And another quantity is this yi hat minus this y bar. So these two, sum them up would equal to this, because this and this could cancel, right? And it's intuitive from this plot. And this quantity can be split into these two parts. And similarly, we can show that this total sum of squares is a summation of this residual sum square and this SS regression sum of square. So these are actually corresponding to each other. If you look at this SST, total sum of square is just the sum of squared of this quantity. And this residual residual sum of square RSS as this squared and then take the sum, and correspondingly this is for the SS reg. And this actually gave us a decomposition of the total being part of unexplained by the regression model, and the other part is what the regression model explained. Okay, this is one important quantity. Well, this is actually the core of what the ANOVA will deal with, but more, I mean, simpler here, we'll talk about the residual standard error that we actually, oops. Well, yeah, I mentioned this RSS is the part that's not explained by our regression model, right? So now we will define this residual standard error based on this residual sum of square. So normally people use this residual sum of square to estimate the accuracy of the model, is which is it just estimates the standard deviation of our error term. So remember that even if our estimates of the parameters were perfect, our prediction would not be. We would always have this error term. This uncertainty comes with the estimation, with the prediction. So that's why we use this error, the standard deviation of the error, to quantify like how close or how certain, how confident we are with our predictions, with our models. So this estimate is roughly speaking the average amount that the response will deviate from the true regression line. So this is like the definition for this residual sum of square, and it's based on this. This is residual standard error. It's calculated based on this residual sum of square. And so basically this RSS divided by n-2. Again, this is the degree of freedom. And if you write this RSS out, it's just like this. So this is important. This residual standard error is the way that we estimate, how accurate our model is. And it used the average amount that the predicted response will deviate from the true regression line. Okay, so this is one. Well, how are we going to interpret the residual standard error, RSE? Okay, I'll just from here I'll just call it RSE. Otherwise, I might mislead you. So the RSE is considered a measure of the lack of fit of the model to the data. So we said it measures the error that deviate from the error, or the model deviate from, the average amount that the response deviate from the true regression line. And more formally, it's a measure of the lack of fit of the model. It measures in the unit of the response value. Because again, if we go back, as the average amount that response deviate from the true regression line, so it's in the unit of the response. For example, if our RSE is 2.5 inches, so even if our model is correct and we will estimate our parameters perfectly, the prediction will still be off by approximately 2.5 inches on average. So this is just how would you interpret the RSE. So whether or not that's an acceptable amount of the error, it will depend on your problem. It would so it could be higher, it could be lower, and whether it's acceptable would depending on like how the data, like how messy the data is. Like when you have some experience working with real data, you know this like roughly what this RSE is. is already good enough, or yeah, that's how you get a feeling of how good this model is. But this RSE is just a quantity that you rely on to evaluate the model you have. Okay, another assessing method is called R squared. This should be familiar to I think to everyone. So also because this RSE is absolute and it would be depending on the context. And now we want to look at this R square, which is called the coefficient of determination of the regression line. We look at this R square so that we get a better feeling of how the model looks like. I mean, easier to evaluate for us because we actually all know this R square would range from 0 to 1. The closer R square to 1, the better. Right? That's why we want to talk about this R square beside RSE. Well, okay, formally, how this R square is calculated. It's nothing but this regression sum square divided by this total sum of square. And this regression sum square is this SST minus residual sum of square. And you can also write it as 1 minus ISS divided by SST. So now you know why this R square always range from 0 to 1. Because like SST is the summation of RSS plus SS regression, right? This value would always be less than 1. So this 1 minus this, and it's always being positive. So this would give us a quantity being within 0 to 1. So this proportion is the amount of the total variability in the data that is explained by the model. It's always between 0 and 1, as mentioned, and it's independent of the scale of y. So this is a main difference compared to this residual, well, RSE, because I always remember this RSE being like always got confused with this RSS. Okay. Oh yeah, even though we know the scale of R square is independent of y, we know it's always from 0 to 1, but it still can be challenging to determine what makes a good R square value. And it's completely depending on the situation. So in general, we mentioned the closer the value is to 1, the more of the variance in the data is explained by the model. So the better the model is. And also there are settings where we know the data comes from a linear model and we expect a value that's essentially 1. And there are settings where a value below 0.1 is still a good model. So it depending on the data and depending on how easy or how hard you can get a model that fit the data well. So again, it depends. So in simple linear regression, R square is also equal to the square of the correlation between y and x. If you calculate the correlation between y and x and take the square, you get your R square. And recall that the correlation is a measure of the linear relationship between two variables. And we mentioned that some small R square can be also a good model, but there are also cases where you see R square being perfectly good. It's very close to 1, for example, in this case, where we get 0.9852, which is absolutely great R square. But if you take a closer look at the data, we have Now we have the scatter plot of y and x. And this y is the US per capita consumption of margarine. And x, what is x? X is the divorce rate in Maine. So by common sense, how could these two be really correlated? But by chance, if we plot these two, they seem really perfectly correlated, right? But it means nothing. Like doing a model like this, giving you a big R square, but this model is not really a good model. We know it. So yeah, just pay attention. Like a small R square may not be as bad as you thought, and a big R square may not as good as you think. So evaluate your R square depending on your context, depending on your experience, like how good the data is and the model. So it takes practice, and you will know the data well, and then you know what R square is a good enough R square. And this small example also tells you how important it is to get a valid model first before we do like all kinds of inference, etc.